Okay, welcome to the screencast for Engineering 122. I'll probably give you a couple screencasts to watch for the Missing Wednesday lecture. The first, though, is that we're going to finish up this clock pendulum with air drag damping, and this is the fourth notebook that you all have downloaded for your in-class work. And this one you'll need to turn in by Friday of this week as a complete item. So we're working with this pendulum that it is a compound pendulum. It has two rigid bodies that are compositely connected rigidly together to make a composite rigid body. One is the cylindrical rod and one is the thin disc. And there are different constant parameters associated with these, the geometry and masses and inertia that are effectively there for the disc. In addition, we have this force, this drag force, that we have modeled as a linear relationship. It's linear with respect to that theta dot term, the angular velocity of this pendulum. So during class, we set up the system, investigated what some of the parameters were. You then started to look at the ideas about how this drag, this linear damping term, which is called viscous damping in the constants, affects the system. And the first exercise had you create a widget that controlled this plot, and you could adjust that viscous damping value from 0, which we would get a non-damped or non-decaying oscillation, and then as that damping is increased, we can see that we can quickly get damped oscillations. This is the under-damped regime that we learned in the prior lecture notes. And as we move forward, it gets more and more damped, until it's hard to notice any oscillations at a certain damping value. That regime, the boundary between no oscillations and oscillations, is the critical damping regime. And then above that we have overdamped. So all of this above that we have no oscillations, but we do see that more and more damping does change the time constant, or how fast or slow the system decays. So more damping, in fact, makes this exponential less steep in that case. You then looked at a few basic visualizations, and you were asked to try some different values to see how that looked from a animation perspective of this pendulum. So you could, for example, change a value up here. If I then change that to 0.5 damping and execute this, I will see that the system stops more quickly. If I make that value very small, 0.005, then I get a oscillation here that does not seem to damp, at least in the 5 seconds of the simulation. There was also this animation here, alternative way to make the animation that gives you some controls. You can advance frame by frame, you can speed up, you can loop it, play, speed it up a lot, slow it down. This can help you potentially if you want to try to get the seconds matching. Sometimes depending on your computer's processor, the timing of the visualization, which I display time there, may or may not match real time. Okay. The next bit that we worked on is I asked you to write a loop here that cycled through multiple values of that viscous damping coefficient. And I suggested from 0 to 5 and do about 30 values. And then you had to fill out this loop for change the damping value, simulate the system, calculate the period, and there's this estimate period function that you have used before, and then append the period to a list of periods, right? So the solution is there. We do get this warning. I can investigate some of the things. I see now that I do get some periods, right? It is populated, but after a period of 2.63 seconds, I start to get not a number. Something went wrong, and that warning that we see here is actually related to why these not a number values appeared. If I plot that figure such that I can plot the damping coefficient values that we used versus the period, we see that it starts with a period of 1 second, and as I increase the damping coefficient, the period of oscillation increases. And then it ramps up quite a lot, and then past a value of 1.5 or so, we don't get any more dots. And that is because our values of periods are these nan values. Right? They are not going to display as a value because it is not a number. So they're absent from the graph. We can see then that two key things is that the period increases with damping. Okay. So if I have a clock that I wanted to swing at 1 second, well, it's not going to do that as it stands with damping added. Now I could adjust the inertia of the clock pendulum to compensate for that for any given drag, and that is what you would do in a design case. But a key thing is that notice how this changes over with respect to the damping, and the fact that we no longer have a value that we can calculate. We've talked about this critical damping line, right? This sort of boundary between oscillations and non-oscillations, and what we are seeing here is the effect of that. So to explore a little more deeply, I made a loop here that uses this for C, T in zip viscous damping values and periods. So what we haven't talked about what zip does. I'll just do that real quick. I have list 1, right? If I have 1, 2, 3, and list 2 for, or let's say A, B, C. The zip function, if I do zip L1 and zip L2, and then I'm going to convert that to a list. All right. So if I run this, notice that it gives me a list of tuples that pair 1 and A, 2 and B, 3 and C. So what happens here in the loop, I can then say for, I'll leave that. Then I can do for item from L1, comma, item from L2 in zip L1, comma, L2 as my list. So what it's going to do, it's going to loop through both the lists simultaneously and then select the first items from each and the first items from the second one and the first items from both, the second item from both, the third items from both. So if I print then item from L1 and item from L2, I can see that I match these up, 1 and A, 2 and B, 3 and C. So that's all I've done in this next loop. I took the viscous damping values that we selected and the periods that you collected. I looped through them simultaneously, and then I used this print function. You can do some nice things with printing. So if I have A equals, or val equals a bird, I'll just make it a string of some sort. You can do, I can make a string here, look at that, change this to bird, look at that And then if I put curly braces, I can replace it using the dot format val. Look at that bird. So if I use curly braces in a string and then dot format, I can pass in a variable, and that will then populate into the string. So that's what we're doing here. There are a lot of formatter things. This is the way to display a certain number of decimal places. This colon 1.3f would display 3 decimal places, and you can look those up in the Python documentation. But here I print C equals a 3 decimal number, a tab, right? That's a symbol for a tab, and then T equals a 3 decimal number for the period. Execute those, and then I can display similarly that for C equals 0, I get a period of almost 1, and then as I increase, my period increases, but then between C 1.552 and 1.724, I have this failure to compute, right? So that means that the boundary between the oscillating and non-oscillating must be somewhere in between 1.552 and 1.724 of this damping ratio. So I have a exercise here. Reuse both the loops from above and calculate the viscous damping values around the location which the period cannot compute, 1.55 to 1.65. But do a linear space values that gives us a finer grained distribution of values between those two numbers, and then try to find a value for C at which the period cannot be computed, that value of C that is likely the one tied to the critical damping value. Right? So you should pause the video here and try to answer that exercise. Once you have it, you can come back and I will type an answer here. Alright, so welcome back. I am going to solve this. It says use both loops from above and calculate the viscous damping. There was one loop, right? This let me sort of just display the values. The other loop it's referring to is the one that we actually do the calculations in. So here, I'm just going to copy this. And the key thing is that I need to change the values that we loop through. So I'll copy this in here. We know that we want to go from 1.55 to 1.65. And it says, excuse me, it says to use 25 values. So we'll change then the number there to 25. So now I'm just going to look at that area. I will calculate those values. I just run the same loop. That executed. And then I am going to copy my second loop as it suggests. And I'll just paste that in a new cell below. And then display those. So now I see my spacing is much tighter on the C values, and that around C equals 1.604 and 608, so we could say that 1.606 is our likely value. So we let me just add one more cell, C, and I'll do a markdown cell here. C equals 1.606 for the proximate critical damping. Right? So that solves that. All right. So C that we have here, if I scroll all the way back up, C is this coefficient, C times L times theta dot. All right. Sorry, I'm drinking tea. The C value is different than the B value from the M x double dot plus bx dot plus kx equals 0 that I presented in the notes. We could, okay. In general, the parameters that we have of the actual model the M, C, and K values in the generalized canonical form are going to be functions of those parameters. So B is actually a function of C, L, D, R, these different parameters. The system class will let you select those values. So here I'm just going to set the viscous damping back to a number that we had at the beginning, 0.2. And system has a function here, canonical coefficients. Right? What canonical coefficients does, let's see if it tells us, returns the mass, damping, and stiffness coefficients in that order. So this refers to the, if I have M double dot X, and in our case, I'll just put the numbers, the coordinates and speeds that we have. It's actually theta, right? Double dot theta plus B times dot theta plus K times theta equals 0. So this is the equation we're working with. There is some coefficients M, B, and K with respect to theta double dot, and theta that we can extract based on the constants that the system has. So the constants are not MB. If I can get it to appear. Right? We have these specific details, the bob mass, the bob radius, the rod mass, right? So for example, the M term in this equation is going to somehow be a combination of the bob mass and the rod mass, right? Because it's a composite body. And we'll see, this will be clear when we construct our own systems. The gist is that I can calculate the M, B, and K of the canonical equation by calling that function. And here I display the B value. So the B value is not the same as the C value in general. Right? But now I presented the damping ratio function in class, zeta equals B over 2m omega n. And that is with respect to this canonical form of the equation. So I can calculate omega n as the square root of k over m. I can calculate VR, which is the critical damping value, 2m omega n. And I can see right now that our damping value is smaller than the value there, so I can calculate zeta, and it is less than 1, so I would expect to see an underdamped oscillation. If I came up here and made this value, we know that the critical damping of C was somewhere around 1.6, so let me just do 1.8, and I'll run through those again. Now I have a value greater than 1, which would give me an overdamped situation. And I think if we try 1.606, we should get very close to 1. So the approximation from our simulations is, there's still some little error there. We don't get quite 1, but we're very close. But we can see that our boundary is there. And you could solve for the C value too that gave you the precise number. Alright, the last bit here is I'm just going to take everything I just typed and package it in a little function that calculates zeta. Right? So it takes the system, and in fact, maybe I'll add this here. Takes the system, calculates the canonical coefficients in BK, and then it returns eventually what zeta is. So, bam! I have a little function there, and that should give me. If I give it the system we're working with, I should get the value. Okay. So now we have a function that we could reuse. We could add that to our utilities.py if we want to use that in the future and import it into other modules. Okay. All right, so that was a little connection to the damping ratio. Let's now explore these regimes, underdamped, critically damped, and overdamped a bit more. So the first one is this zeta is less than 1. okay, and this is the underdamped motion. We would see oscillations, but those oscillations will decay in an underdamped scenario. Right, so your first exercise is to create a single plot that shows the free response at these different viscous damping values, and I have an error in my notebook there. And I give the suggestions at 0, 0.008, 0.2, and 1.6. Use an initial angle of 5 degrees and an initial angular velocity of 0 degrees. Include a legend so that it is clear which lines represent which values, and use a loop to reduce the amount of typing needed. Okay? So you should pause the video right now and attempt to create the plot as described. You can always click on the solution to under the 3 dots if you need to do so. So pause the video and then we will come back and I will type the solution. Alright, welcome back. Let's attempt this. Okay, so how am I going to do this? I need to try some different viscous damping values. So I'm just going to say v-vals equals, and I'll make a list of those. Right, 8.2, 1.6. And I'll start there. And we need a basic figure. So I'm going to do figure comma x equals plt dot subplots. And I'm going to do it all in one figure, so I don't need to give any arguments to subplots. That'll give us a base figure. Right? If I execute that, I just get an empty figure. Now, we're going to set the we're going to use the same system. So the initial angle I can set by selecting coordinates, and let's just check the word there. It is angle. So I'll do set the angle, okay, to 5 degrees. So np dot degree to radian, right? These always have to be in radians, but I can just bam, give it a 5 degree, use my little function, and then let's make sure that the angular velocity equals 0 degrees per second. So this is going to be radian per second, right, that we actually pass in radian. Okay? So I set the initial values, and now I want to loop through each of those values and add a new line to the plot. Alright, so I'm going to do for C in, and I guess I should have done C vals. Let's do that. Change that to C vals. So for C vals, for C and C vals, sys dot constants is where this is stored, and we get the viscous damping term. I set that to C equals C. So I set that value. Now simulate the system. We get sys dot free response. We'll do 5 seconds. Okay. It doesn't look like I gave a specific time. For 5 seconds. Now, for that value of C, I have simulated it, and I've calculated a trajectory. I can plot on the axes. AX dot plot, and I give it the x value, which is going to be traj dot index, which stores all the times, and then traj dot angle, right? Plot shows the free response. We'll plot the angle. Right. So this, if I execute it, gives me, for the 4 values, I get the lines. All right. So let's add a few niceties so we know what our plot is. I'll do ax dot set x label to time in seconds. So ax dot set y label, and that's going to be angle, and we're plotting it in radians, right? That's the default output there. And let's add a legend, right? So if I do ax dot legend, there's a couple ways to do this. One is in the plot call, you can add a label. let's do that. Label equals, and I can use our string formatting. I can say C equals doo-doo, and here I'll do inside of the colon 1.2, right? So I'm going to give 2 floating point values, and then I format and I give it the C value, and then that'll label each line, and then I can just call legend here. Okay. Here we go. We've got a nice plot. Maybe one thing, let's change the angle to degrees, because I have a hard time thinking in radians. So we'll do np dot radian to degree, the opposite, up here. Bam. And then I can change this to degree. See what we got there. So it looks like we're right. We have an initial angle for all of the simulations is 5 degrees. Okay. And now we can see what happens as we increase the damping value. So for C equals 0, this is the undamped case. We get the blue oscillation that does not decay. And then as I ramp up the orange line, we have some decay, the green line much more decay, and then finally C equals 1.6 gives us something that looks like it has no oscillation, but we are under that 1.606, so it does. If we zoomed in, you maybe be able to see a slight oscillation. It's going to be hard to discern though, but yeah, here's a little bump, right? So we can just barely get a estimate of a period at that point. You can see it more clearly as you zoom in. Okay, so here is the underdamped regime, and we cycled through some values that brought us up to the critical damping point. Okay. The next exercise is to look at this critical damping value and examine precisely what that is. So make a single plot of the angle trajectories with the viscous damping set to 1.67 and an initial angle of 0.1 degrees. And then finally plot 3 lines here, but change the initial angular velocity to these -10, 0, and 10 degrees. So we're going to look at how the system behaves if we are at the critical damping, but we give it different initial angular velocities. So you need to pause at this point and work on that solution to make that plot. And you can use the prior plot to give you an idea how to do that. Okay, welcome back. I am going to now solve this one for us. Okay, and it's going to be similar. We need to take the system and get it sort of set up. So I'm going to set the constants. And let's just double check. We had calc, sys.constants, viscous damping. Let's see what we get here. If I set it to 1.67 and then I calc zeta of that system, should get 1. Very close to 1. Okay, so very close to 1. So we're pretty much at the critical damping. If I added some more decimal places to that 1.67, we could get it precisely there. But for the purposes of this, we are at critical damping. All right, so I set that. Let's set the coordinate angle to degree to radian 1.0, and then 3 lines with the initial velocity. Okay, so we're going to cycle through these initial angular velocities. So I'll say ENG bell valves, and we're going to do I'm going to do np dot degree to radian, and I can do it of the whole list: -10 degrees, 0 degrees, 10 degrees, and that will convert all of those to radians. And then let's loop through those for ENG velocity in ENG velocity vowels. Sys dot speeds angular velocity equals ENG. Yeah? So we set that. Now we simulate. Treg equals sys.free response for 5 seconds. Yeah? You'll probably copy some of the code up here. Let me just grab the plotting line, the legend, etc. Copy that in. So we plot the time, which is at dot index, convert the angle to radians, and now we're changing omega, and I could do omega. If I do this latex / omega, I think I've got to make this a raw string for it to, the Python doesn't like backslashes in their strings. And then I can provide my ENG velocity value, and we want to convert that also to degrees. So np dot radian to degree. And time, angle, everything's the same. Let's see if it works. Oh, I forgot to create a new figure. I plotted it all up on the prior figure. So, I need to copy this line. Create the figure. Right, so we want a new figure, not plotting the old one. One thing I noticed is to do this LaTeX, actually I need maths, dollar signs around that. Okay. So here we go. The initial angle we've set to be 1 degree for each system. But we give a different initial angular velocity. For the blue, it's negative, so we see that it decreases in angle first. For the green, it's positive 10. It's going to cause an increase in angle. And then for no angular velocity initially, it is just going to decrease down to 0. Right. So here you can get different behavior, right, with this critical damping value. They're not all going to look the same, and we can see that omega 10 gives a slight, there could be potentially a period connected to that. So maybe we do need a better, more precise value of zeta, but I'll leave it at that. Anyways, this shows that the critical damping behavior, depending on if you give it positive or negative initial angular velocity or 0 initial angular velocity, that you can get different behaviors here for that critical damping for the same system, same initial angle condition. Right? Last one is the overdamped, and we similarly are going to look at this. This is the zeta greater than 1, and I suggest create a single plot with a viscous damping value at 2. Right? So we know that this is going to create a zeta greater than 1, and then these 3 sets of initial conditions. So here's an exercise. You set the different pairs of initial conditions and see if you can come up with a plot to look at how overdamped with the same damping value will then give you different results. So pause here and attempt to write that function. Okay, welcome back. I am going to copy my function from my code from the last time and just work through and edit it. Okay, so we want to do 2.0 for the damping constant. Let's print this so we make sure that we do get a zeta greater than 1. And I am going to loop through two pairs of things here, so I could use the zip function that we learned earlier. Right? So I need theta and theta dot. So I'm going to do ENG vowels and angular velocity vowels. Right? I'll do NP, degree, to radian, and then I'm going to have 1, 0, and -1, and then 0, 10, and 0. Right? So I set up these pairs like I did. I want this is going to now go inside of my loop. Right. Go ahead. We're going to set both the angle and the angular velocity. So I'm going to have an angle and an angular velocity. And how do I get those? Well, ENG, comma angular velocity, and then I use my zip ENG vowels and ENG vowels. All right, so I'll loop through those pairs, set them, simulate it, and now I need to get a good label. So we've got two things here, theta, the initial theta and the initial omega. So let's sort of set up the string here right above it. So I'm going to say template equals the string, and then I'm going to add theta equals 1.2f comma omega. Okay, so now I have two curly braces, so I'm going to have to pass in two values. So I'll do that the label equals the template, format it, and I need NP, radian to degree, ENG, and ENG val. And I think that's it. Let's take a look. NumPy float64 object has no attribute to f. What did I do? Oh, I forgot my colon in that template. Here we go. Got the result. So I've got the overdamp situation. We do not have oscillations, but we try different pairs of initial conditions. So here, the blue line, I start at an initial angle of 1 degree and no angular velocity. So we'll see that it just decays rapidly to 0. The second scenario is the angle starts at 0, but I give it an initial angular velocity of 10 degrees. So I get a positive increase in angle, and then it decays back to 0. And then I start at -1 degree, no angular velocity, decays to 0, but from the negative direction. Let's add a plot here. Let's make it a 2x1 subplot, and then I'll call this axes. Right? I'm not going to add. Oh yeah. Then I can do axes, the first plot of the subplot, and let's copy this. Actually, just the first line. And on the second axis, I will plot the angular velocity. I think that'll work. Alright, there we go. And then my legends, I need to fix all this stuff. This is going to go in axis 1. This will go in axis 0, the angle. Need angular velocity. Degree per second, and that's going to go on 1. And then we'll do axes. Let's just put the legend on the first one. Alright, there we go. Now we can look at both of those, the angle and the angular velocity, theta and omega, and sort of double check that our initial conditions. So initial on the blue and green line for omega is 0, and on the orange line is 10 degrees. And we can see that the time derivative of theta, omega, has similar behaviors, but these are related by the derivative, and we can change either one to get effects in the other in terms of the initial conditions. Okay. All right. So the gist of this is we've examined how these systems behave in underdamped, critically damped, overdamped, and undamped scenarios, and looked at how you can get different type of responses that are all critically damped or all underdamped or overdamped, depending on the initial conditions that we set for the simulations. All right. So to wrap up everything here, we have looked at this effect of linear damping on some kind of real system. We noticed that there is this critical damping boundary where we have oscillation and not oscillation. We saw that the period of oscillation will increase with damping, right? So damping affects the period, and that you will have to be aware of when designing and thinking of these systems. We looked at the damping ratio here and how to calculate that, created a little helpful function so we could evaluate what regime we were in. And then we looked at different behaviors in the different regimes, and you can try new values and see more behaviors in that case. Okay, that's the end of this notebook, and you should turn this in Friday as one of your classworks.